Have you ever wanted to understand one of the most incredible discoveries in mathematics? Today, we're going to dive into the big idea of calculus. Our goal is to understand how we transition from the static world of algebra to the dynamic world of motion and change. By the end of this video, you will be able to, first, define a limit and explain why it's a foundational tool in calculus. Second, understand the core concepts of derivatives and integrals. And third, grasp the fundamental idea that these two concepts are inverses connected by the Fundamental Theorem of Calculus. So are you ready? Let's begin. Let's start with a problem that algebra alone can't solve. Imagine a car traveling at a constant 60 miles per hour. Easy. Distance equals rate times time. After 1 hour, you've gone 60 miles. This is the simple world of algebra. But what if the car is accelerating? It's speeding up. How fast is it going at the exact moment it passes a certain point, say a mile marker? Algebra can only tell us the average speed over an interval. To find the instantaneous speed, the speed at that precise instant, we need calculus. This is where the first big idea comes in: the limit. A limit is the value that a function approaches as the input approaches some value. Think of it as getting infinitely close, but never actually touching. In our car example, we can calculate the average speed over smaller and smaller time intervals around our mile marker. A limit is the speed we approach as that time interval gets infinitely tiny. It's the ultimate zoom-in tool. This idea of instantaneous change leads us directly to the first pillar of calculus, the derivative. A derivative measures how one quantity changes in response to another. Geometrically, it's the slope of the tangent line to a curve at any given point. Let's go back to our car. We can graph its position over time. Since it's accelerating, the graph is a curve. The slope of a line is just the rise over the run, or change in y over change in x. If we draw a line connecting 2 points on the curve, the slope of that secant line gives us the average speed between those two times. Now imagine using a limit to shrink the distance between those 2 points until they are infinitely close. The second line becomes a tangent line, touching the curve at only 1 point. The slope of that tangent line is the derivative. It's the instantaneous rate of change, or in our analogy, the exact speed on the speedometer at that precise moment. Calculating these derivatives from scratch can be a lot of work. This is why calculus is so powerful. Mathematicians have given us amazing shortcuts. Let's see one in action. Our goal is to understand how we can find a derivative quickly, so we can feel the magic of these rules. Meet the power rule. It tells us how to find the derivative of a function like x to the power of n. The rule is incredibly simple. If our function, let's call it f of x, is x to the power of n, its derivative, f prime of x, is found by taking the exponent en, bringing it down to the front as a coefficient, and then subtracting 1 from the original exponent. Let's try it with a classic example. Suppose we have the function f of x equals x squared. In this case, our exponent n is 2. To find the derivative f prime of x, we bring the 2 to the front and then subtract 1 from the exponent. 2 minus 1 is 1. So the derivative of x squared is simply 2x. That's it. We just found the instantaneous slope of the curve y equals x squared at any point x with one simple rule. That's the power of calculus. Now, let's explore the second big pillar of calculus, the integral. We've learned how to measure an instant. Now, how do we measure the total accumulation of something over time? The integral is the tool for accumulation. Its most common application is finding the area under a curve. Geometrically, it's the area between a function's graph and the x-axis over a specified interval. Let's return to our car. If the graph of the car's velocity over time is a curve, how can we find the total distance it has traveled between, say, t equals a and t equals b? With algebra, we could only find the area of simple shapes like rectangles or triangles. But this area is curved. Calculus solves this by, once again, getting infinitely close. We approximate the area with a series of rectangles. We find the area of each one and add them up. Just like with derivatives, the magic happens with a limit. We imagine the number of these rectangles increasing to infinity and their width shrinking to 0. This limit of the sum of infinitely many, infinitely thin rectangles gives us the exact area. This area is the integral. In our car analogy, the area under the velocity curve is the total distance traveled. It's the car's odometer reading. So, we have derivatives for instantaneous change, the speedometer, and integrals for total accumulation, the odometer. It turns out these two ideas aren't just related, they are inverses. You can undo a derivative with an integral, and vice versa. This is the incredible statement of the fundamental theorem of calculus. To illustrate, imagine you know your car's speedometer reading at every instant in time. That's a derivative. By integrating that instantaneous velocity, you can reconstruct the exact odometer reading or the total distance you've traveled. You're starting from the rate of change and working backward to the total. The reverse is also true. If you know your total distance traveled as a function of time, you can differentiate it to find your instantaneous speed at any moment. You're taking the total and working forward to find the rate of change. The fundamental theorem is what makes calculus a coherent, elegant system, not just a collection of tricks. It reveals the deep connection between slopes and areas, between rates and totals. Let's quickly recap what we've discovered today. We saw that algebra struggles with motion, which led us to calculus. We learned that the limit is our tool for getting infinitely close, a necessary step for defining instantaneous concepts. The derivative measures instantaneous change, like a car's speedometer. We even saw a quick win with the power rule to find a derivative. The integral measures total accumulation, like a car's odometer. It's the area under a curve. And finally, we connected these two powerful ideas with the fundamental theorem of calculus, revealing them as inverse operations. Calculus isn't just about formulas. It's a way of seeing the world, a language for describing change. It's everywhere, in science, engineering, economics. You've now taken the first step to understanding this incredible subject. I hope you feel the excitement of this big idea. The journey is just beginning, but you've cracked the code on its most fundamental concepts. Keep exploring, and you'll find there's nothing intimidating about it at all. Thanks for watching.